This webinar is being recorded and will be published on the FECM website. If you do not wish to have your voice recorded, please do not speak during the call. If you do not wish to have your image recorded, please turn off your camera or participate by phone. And if you speak during the call or use a video connection, you are presumed to consent to recording and use of your voice or image. So please also, if you could, mute your devices, and we will begin shortly. Thank you. So I'll just start by saying thank you to those of you that are here today. And we are not doing this as a webinar because I wanted it to be more of a teaching experience. And but if you have to step out early, because this is pretty long, it's a 90-minute session, and hoping to get through a lot of content in the first hour and then leave a half an hour just for open Q&A. And so rather than having, the inability for folks to come off of mute and camera, we wanted to make it more of a relaxed discussion, especially at the Q&A stage. But if you do have, a clarifying question as I'm going through the content, please just let me know, and I'm happy to try and add clarity. But the way that I'd like to do this is really to go through the presentation. So it'd be great if you, again, have your microphones on mute, and then we'll save the Q&A for 4 to 4:30. And I'll just warn you that it may feel a little academic. So, this is definitely me wearing my teacher hat today. And the rationale for doing this is because I just know that there's so many across broader DOE that's working in this space. And I've had an opportunity to have been in this space since it really began. And so I thought maybe it would be a good service to just go through some of the fundamentals and the challenges associated with the scale up of direct air capture and share it and this information with the broader DOE community. And so I'm going to start here. This is, some of you are already aware of this, that our Office of Fossil Energy and Carbon Management underwent a reorganization in the first year of the new administration. And a lot of what we were doing is really aligning the investments across FECM with the updated and more recent climate goals. The most significant one being net zero greenhouse gas emissions by mid-century. And then the two that we're hoping to hit along the way, 50% emissions reduction by 2030, which is less than a decade away. And then CO2 emissions free power by 2035. If you're interested in learning more about FECM's mission and also our recent strategic vision document, you can download this from our website, DOE FECM resources under strategic vision, and you can learn more. But the work that we're doing in FECM is, from an R&D perspective, is really in two different offices. One is associated with managing the carbon pollution from our dependence on fossil fuels, whether it's for power generation, for industry, and also recognizing that we need to take CO2 out of the atmosphere. So direct air capture of CO2 from the accumulated pool in the atmosphere, and then managing that CO2, whether it's capture from a point source or directly out of the atmosphere, managing it in a way that it doesn't come back into the atmosphere. And so geologic storage, I'm going to talk about some other pathways today too. The second R&D area that we're focused on is how we extract fossil fuels out of the earth today, whether it's oil, gas, or coal. A big part of the effort there is associated with methane quantification and mitigation, and also using a lot of these unconventional feedstocks associated with legacy impacts of fossil for critical minerals and rare earth element production. And then finally, throughout all the work that we're doing, there's a thread of advancing justice, labor, and broad engagement from communities to stakeholders. When we think about all of these elements, and thinking about really carbon management more broadly. We recognize that there's no silver bullet and that all of these approaches are going to be required in order for us to achieve deep decarbonization and ultimately net zero greenhouse gases. And what I'm going to talk about today specifically is direct air capture. And I will get into a little bit direct air capture as one of a portfolio of tools that we have across carbon dioxide removal approaches. So before kind of getting into the content, I thought it might be useful to share with you my history and path into this field. And so I started in this field back in 2008, specifically in the field of direct air capture. Of course, earlier than that, point source carbon capture. But in 2008, I was asked to be on one of the authors on a report that was from the American Physical Society, and that was led by Rob Sokolow, who's an emeritus professor at Princeton now. And you can see off to the left there, the bottom left, you know, we had Bill Brinkman, we had Arun Majumdar that were kind of part of these efforts, and then they got pulled into the Obama administration at that time, but a lot of authors, you know, that really were getting started into this field. Now, what we were asked to do in that study, in that APS report, is to understand or to be able to quantify the costs of direct air capture based on existing technology at that time. And so we had to look at the chemical engineering literature and understand separations processes and take what we know for more concentrated streams and how can we apply that knowledge to direct air capture, because that's how new it was. And at that time too, there was a little bit of, to be honest, back in 2008, we could have just invested all in deep decarbonization. And maybe at that time, if we scaled that up quick enough, we wouldn't be in the situation of needing carbon removal today. But we've really surpassed that point, and now it's going to be a critical tool to achieving net zero. Back in 2008, that wasn't the case. And so we were really asking, you know, if you only have so many dollars, should we really be investing in this technology and what's it going to cost? And that was kind of the point of the study, is to just really figure out, you know, a robust techno-economic analysis of direct air capture. In that process, which took 3 years before we finally got the report to be published, and by the way, there was a lot of pushback to that report being published. A lot of folks didn't want to see that coming through because they saw it as a moral hazard at the time, and that it would slow our progress in deep decarbonization. And so, but once that, you know, while I was working on that, and at the same time, I was developing a course. I was a professor at Stanford at the time, and I was developing a course on carbon capture and storage, and recognized that there wasn't a good book for my students. And I was always pulling resources together. And again, I'm a chemical engineer by training, and a lot of this is separations, and it's chemical engineering and some mechanical engineering. And so I decided to develop the first textbook on the topic. And because I was really also engaged in the direct air capture conversation, if you look at the textbook that I wrote, Carbon Capture, there is a thread of direct air capture throughout. And there's a constant reminder of how much more difficult it is to separate CO2 from a dilute stream like the air compared to some of the more concentrated sources. And then after that, I got engaged with a couple of reports that came out of the National Academy of Sciences of Engineering and Medicine. In 2015, we had a series of 2 reports. Right here is one of them. At that point, and again, this is a little bit of history, at that time, approaches like direct air capture were termed geoengineering. And if you're familiar with that space, geoengineering is more, you know, these methods to change the reflectivity of the Earth, injecting particles into the stratosphere to induce cooling. And so a group of us got together, and that climate intervention report was led by Marcia McNutt. And half of our group was focused on albedo modification, changing the reflectivity of the Earth, and the other half was focused on carbon dioxide removal approaches. And at first, you know, the effort was joint, and we made a decision as a group to actually, at the end of the day, publish 2 reports, because the consequences of each of these types of tools, whether it's reflectivity or whether it's carbon removal, the potential negative consequences of each is extremely different. And so we did not want to mix these. And we also didn't want to keep using the term geoengineering as that kind of umbrella term. And so collectively, we decided on this new term, which really has not taken off, but it's climate intervention, because the idea is that you have two knobs to intervene with climate change. One of them being to remove CO2 or greenhouse gases from the atmosphere. And the second one is that knob of changing the reflectivity of the earth. And so ultimately, at the end of the day, there were two reports. And if you want to learn more, you can kind of check those out. That was in 2015. A few years later, asked again to say, specifically on carbon removal, and now calling it negative emissions technologies coupled to reliable sequestration or storage. I was approached by National Academy of Sciences again and asked to be part of this new report. And this was led by Steve Pacala, who's a professor at Princeton. And that leadership was really critical, because at the end of the day, what we aim to do with this report is to provide a blueprint for the federal government so that they knew exactly across which agencies, whether it's USDA, NSF, DOE, investments should be made, how much, and at what level of technological readiness should we be investing at. So imagine, this blueprint of the scale, the sector, topic, TRL, government agency, and recognizing it's a call to action of all of our agencies to really chip in. And so it was a significant effort, and it's really about a research agenda. And then also at that same time, I recognized that there was a gap in terms of researchers and where they could submit their findings all in one place. And so I worked with the open access journal Frontiers. I was a specialty chief editor for their energy section previously. And I said, and I was stepping down from that role. And they said, we'd like to keep you. And I said, well, here's a field that I would be excited about. Here's a field that I think there's a gap, and that's carbon removal or negative emissions technologies. And I don't want it to be coupled with energy. I want it to be coupled with climate. And so the Open Access Frontiers Journal in Climate, we started and launched this new journal within that framework on negative emissions. And I pulled my colleague from Heriot-Watt University, Phil Renforth, in with me. And it's a good thing I did, because it's still going strong while I'm, on leave as a professor, on leave from all things except what we're doing here at DOE. And then at that same time, actually, it was from 2017 to 2020, I also started an effort recognizing that we needed to really teach carbon removal. We needed a tool to be able to get everybody up to speed. We had our first workshop was held in Italy, where we got a bunch of folks together, about 60 thought leaders from Asia, North America, and also Europe. And when you look at this field of carbon removal, it's agriculture, it's soil science, it's forestry, it's oceans, it's chemical engineering, it's geophysics, it's petroleum, it's social science, it's economics, it's everything. And so you get us all in a room, and we're using different language, we're using different terminology, we have different definitions of what permanence and durability means. And so the first question that we asked all of ourselves in that meeting was, if we're going to develop something, who's the audience? And we recognized we were the audience, because we recognized that all these scientists and researchers needed to start speaking the same language, and we really weren't at that time. And so that was the start of the CDR primer. And because I wanted this document to be accessible, I wanted it to be accessible to somebody who's mid-career and making a change, and they want to invest, every ounce of what they're doing every day into climate. And I wanted them to be able to find their path in this book. And also, a high school student or a college student just getting started. And so the question is, how do you write a book to those levels, especially when you're coming from experts in these different fields? And so at the end of the day, the way that we did that is we engaged junior thinkers in this space, postdocs, researchers and students. And we even had a group of undergraduates who read the book start to finish and provided critical feedback on what was complicated, what couldn't they grasp, what couldn't they understand. And it was a working group, and they would read and have assignments and then come together and have those deep discussions that would take hours. And they'd provide that feedback. So we had this constant feedback loop. We met 3 times, and once in North America, once and twice in Europe over that time. And then in 2021, we made it available open access on the web. And we took a year to provide more critical feedback as people started to read it and play with it and digest it. And now, just a couple months ago, it's available in hard copy, and it's only at the cost of making the book. And so 40 authors at the end of the day engaged in this process, where the thought leaders in the space from all parts of the world were providing the critical feedback to the junior folks that were actually holding the pen to write the is all of this work and effort that we're putting in going to have impact? And I'm happy to say it has, because we were able to launch the carbon negative shot in November last year. There are so many of us at DOE, they're collectively working together to move this work through. One of the biggest, I would say, challenges associated with this portfolio is that the nature-based approaches, they are not, we don't have the tools to make them as quantitative as we do with direct air capture with chemicals, coupled to geologic storage. We have 45Q, the federal tax credit, that incentivize at $180 per ton direct air capture. Our team provides technical expertise in FECM to the US Treasury in order to really be able to do the math and make sure that carbon accounting is accurate and consistent. We also have the Class 6 well permits from EPA, and that process has embedded within it monitoring, reporting, and verification to prevent leakage of CO2. We don't have those same rigorous quantification tools in place for when we choose to plant a tree and in a location that we know the risk is low in terms of forest fires or insect damage. We don't have a way to think about increasing soil carbon storage through agricultural practices that could ensure that the carbon is stored and that it's additional carbon removal, and for how many years, and what does that look like? And so a big effort with our carbon negative shot is catching up these other approaches to the quantifiable, durable metrics that we have for direct air capture coupled to geologic storage. And then, because at the end of the day, a lot of energy and attention on direct air capture, but there isn't a silver bullet solution. We need to make sure that all of these approaches are robust. And also recognize that a lot of the nature-based approaches, there are significant ecosystem benefits associated with these. If we're investing in improving the way that we manage a forest such that we increase the carbon uptake of a forest, we're also reducing the risk of that forest going, reversing from a sink to a source in terms of a forest fire. So significant ecosystem benefits associated with the broad range of the nature-based approaches. So now I think the rest of my talk here is really going to be about direct air capture more specifically, but wanted to mention a little bit some of the energy in the space, because you're reading it, you hear about it. The momentum is pretty significant right now in this space. There's an article up there in the Atlantic by Robinson Meyer, that's talking about we've never seen a carbon removal plan like this before, in reference to the frontier, $925 million of voluntary removals. In other words, paying for the capital investments for companies to do this that don't exist yet. Paying in advance to helping with those companies to be able to invest and actually be able to demonstrate the technologies. Looking, there's lower carbon capital. And this is a company that's led by Chris Sacca. And Chris Sacca is a venture investor, a lawyer by training. And you might have heard of some of, his successful investments, early stage technologies like Twitter, Uber, Instagram, Kickstart. And he also contributed $350 million into this effort. And there's a link to, his website. You should go check it out. He really talks real about all of this work. And that's titled Cleanup on Isle Earth. And then Transform to Net Zero. 8 companies working together to accelerate business action toward a net zero economy. You've heard about the forward thinking and not just thinking, but actions of Microsoft. And there's a number of other companies that are in this space, not just investing in deep decarbonization, but recognizing to achieve net zero. And a lot of the corporations, these are scope 3 emissions that they don't have control over. And so in order for these corporations to achieve their net zero greenhouse gas goals, they have to rely on carbon removal to counterbalance those emissions that they don't have control over. And so just a lot of momentum and activity in this space. So which also, and I'm going to, there's going to be a sprinkling of a number of different references throughout. And this first one is an image from chapter 1 of the CDR primer, which my hope is that we think responsibly about this tool and that we don't see carbon removal as a tool to offset emissions, that we actually have technologies to avoid the emissions. And so, for instance, if we have carbon capture coupled to a natural gas-fired power plant that's expected to persist through mid-century, we should decarbonize. We should do CCS on that and not see carbon removal as also having to take on the burden of those emissions, because that's what net zero means. It ultimately means that for the carbon we put into the atmosphere, we're going to have to take back out. And some, push back against that and say, but, the nature-based approaches like forests and unfortunately at the expense of oceans and ocean acidification remove roughly half of our emissions every year globally. But our reliance on that is teetering as we see more forest fires and also at the expense of ocean acidification. Our reliance on those nature-based approaches, which also goes back to my point of like, how can we make those more robust? And I won't get to talk too much about it today, but there's ocean removal processes that actually lead to the co-benefit of reducing ocean acidification, improving the health of our oceans. So here, what we're looking at is rather than a top-down calculation, it's really a bottom-up calculation. And this is really thinking about what are the sectors that are truly hard to decarbonize today, and the background of the calculations and where those numbers are sourced from. You can look at all of that in chapter 1 of the primer. In the United States, we emit roughly 5.8 to 6 gigatons of CO2 equivalent per year. When you go bottom up and you look at agriculture and you look at parts of the aviation sector, long-haul trucking, shipping, or parts of the transportation sector, aviation, long-haul trucks and shipping, it adds up to around a gigaton. And so, and globally, of course, more than that. And again, you can kind of see the details more in the primer, which is very global heavy. And so the idea there is that today we're on the order of thousands of tons of removal. And if we need to be at gigatons to achieve net zero by mid-century, that's 6 more zeros in less than 30 years. So we need to invest today if we're going to get there in time. And we need to be recognizing that maybe it's not tens of gigatons, but it's certainly gigaton scale. Now, this also goes to the point of not seeing carbon removal or direct air capture as a means of offsetting industries and sectors that we have technologies to decarbonize today. And so the plot on the right-hand side is the CO2 concentration in a given gas mixture, and then plotted against the minimum work. So the minimum work might be new to some of you. What that means is we can combine the first and second laws of thermodynamics in order to calculate what is the minimum energy required to pull CO2 out, to separate CO2. The only things you need to know, there's 3 pieces that you need to know to do this calculation. And if you're interested in doing these, I show how to do it in chapter 1 of my textbook. And it's the first homework problem with my carbon capture course. You need to know the starting concentration of CO2, and you kind of have an estimate here on the x-axis. And when you look at, for instance, separating hydrogen from steam methane reforming, it's more concentrated. When you look at cement and steel production, it's a broad range. It depends on what the fuels are, but the fuel is often mixed with the mineral that you're working with. So if it's cement, you're calcining limestone. If it's steel, you're reducing iron oxide. And so it's a mix of those minerals with the fuel to get good heat transfer, which means that the concentration in cement and steel is actually boosted compared to, say, a natural gas exhaust stream from a power plant. And so in order to calculate the minimum work, the three things are that CO2 concentration, which you see here on the x-axis, and then also how much are you capturing? 70%, 90%, and then finally, what is the end purity of the CO2? If you need it to move it in a pipeline or a truck, or you're injecting it deep underground, it needs to be high purity, 99% plus. And so those boundary conditions dictate what the thermodynamic minimum is for a given separation process. And why that's so powerful is that if you have a new technology and you could look at their costs and its operating costs, OPEX, forget about the capital for a minute. It's just the operating. The operating costs are based on the energy for the separation. And so you can kind of back out depending on what energy resources they're assuming, whether it's low carbon energy or fossil with CCS, you can still back out the energy required for the separation. If they claim to be lower than the minimum work, they're wrong, and it's a false promise. And so it's a very powerful calculation to ground truth, the energetics, and ultimately the operating costs of any application in any technology. And then what you can see here, these are just kind of rules of thumb, for these different concentrations too, just good benchmarks. And you see that as we get further and further dilute, as you move left on that axis, direct air capture is just significantly more because it's so dilute. And when we look at the nth of a kind costs, and I want to be really clear, nth of a kind, not first of a kind. This is just a simple model, in some cases using a bit of Aspen for the technical data that we do have for some of these systems. But really an nth of a cost model based upon the concentration and the minimum work estimates. And so at the end of the day, direct air capture is going to be more expensive. It's going to be more energy intensive than these concentrated sources. And we've really got to save it for the hard to decarbonize sectors. So I wanted to talk about some of the common questions that I hear in this space and try and debunk some of the misconceptions too. So the first one is, what separation technologies are applicable to direct air capture? And this is, one might say this is a chemical engineering question, but I'll quickly make it, not so chemical engineering. But first off, in chemical engineering, there's a whole sector called, or subfield called separation science. And the different separation processes include absorption, AB, which is solvents or liquid-based processes. And in this case, it's involves a base. And because bases are corrosive, you then only can put so much in the liquid. So most of it's water. So you're having to spend a lot of energy heating up water. Adsorption, so that's AD. In Latin means two, like on a surface. And so solid sorbents, you can think of your Brita filter. And then membranes is another separation. Membranes are a wonderful thing, but they only work if you have a high driving force. And so direct air capture CO2 is too dilute for membranes to work, but you could have reactive membranes. But that case, you're really going back to having chemistry. So it's kind of disguised in the framework of a membrane. Cryogenic distillation takes a lot of energy to do that, and you hardly have any CO2 in the air, so that's not so good. The last one, crystallization, is a separation process, also known as mineralization. And that is there are hybrid approaches out there that we'll talk about carbon engineering a little bit that does both. It has a hybrid approach where it's using a solvent, and then it has a crystallization step as well. And so due to the low driving force of CO2 in the atmosphere, at the end of the day, you need chemicals in order to do this. You need a chemical reaction. And so passive membranes, distillation are out. And that's why we often hear about liquid solvents and solid sorbents being the technology options. And again, mineralization and reactive membranes, more nascent. Good rules of thumb too, when you think about CO2 and its dilution in the atmosphere, it's 100 times more dilute than the CO2 in a natural gas exhaust stream, 300 times more dilute than a coal exhaust stream, 500 to 600 times more dilute than the cement or blast furnace exhaust, 1,000 times more dilute than the CO2 from a steam methane reformer, 2,100 times more dilute than if we were to separate CO2 from a bioethanol production or fermentation. And so you might ask, okay, that's interesting, but why is it important? This is important because we're actually going to talk a little bit about flux. And the importance of flux is that whatever your technology is, your separation technology, and you have CO2 in some gas mixture at the interface, in that technology, whether it's a liquid solvent or sorbent, the CO2 has to diffuse in air or the gas mixture. It has to overcome the barrier of going through the interface. It has to then diffuse again. In liquid, it's slow. In gas, it's faster, to find the chemistry at which point it reacts. And how fast the CO2 moves across that interface, and flux is defined as an amount of CO2 that moves across the interface per unit surface area. So if you know kind of that flux, you can back out the surface area. And then backing out that surface area gets you an idea of the capital intent, the capital expense, because it gives you an idea of how much surface area do I need to create in order to ultimately achieve a certain capture rate of CO2. So these X's can also translate to that much more surface area at the end of the day. This isn't written in dilution, which means that if I were to compare, say, for ease, the surface area required to take CO2 out of the air combined to steam methane reforming, my surface area would have to be 1,000 times greater to capture the equivalent CO2 from the air. So that's the idea there. For natural gas exhaust, my surface area needs to be 100 times greater to capture the equivalent CO2. And we're going to see this in pictures in a little bit too. So I want to take the next step here to look at what are some of the differences of capture from a point source versus direct air capture in terms of their designs. So this is a nice picture of an absorption AB solvents absorption column. This is the Petronova project that was funded during the Obama administration. One of the three, I think from a technology perspective, very successful demonstration, capable of capturing up to 1.4 million tons of CO2 per year. So this column is 115 meters tall. And I'm going to talk a little bit about what happens inside. And so I'll first say that the solvents, the first patent was filed by Bottoms in 1930. And the reason why we know how to do this is because we need high purity food grade CO2 for the food and beverage industry. And so we've known how to do this for quite some time. So, and by the way, designing these columns is all the work of chemical engineers. You learn how to do this in your senior design class as an undergraduate. And so when we look at this column, what you see is there's these different horizontal lines, and we call those stages of separation. And these columns are packed with packing material that allows gas and liquid to go through. But at the end of the day, what you really want, the liquid goes in and it's pumped through the top, down through the top, and it trickles across the packing material. The gas is essentially bubbled up through, and you either, depending on the pressure drop, how much energy you have to overcome in the column, you either have to use fans or blowers. And so you're essentially bubbling the gas up through, and the liquid is falling through packing material. At the end of the day, what you want to try and achieve is as much gas liquid interfacial interactions as you can, because the point is that you want the CO2 that's in the gas to leave the gas phase, go through that interface, and find the chemistry to react with. So what ends up happening as you move up the column your gas becomes cleaner and cleaner of CO2. As you move down the column, the liquid becomes more and more saturated in CO2. But the driving force is key. And what I mean by driving force is, if you've got a bunch of CO2 on one end and you don't have any on the other, it's always going in the direction of equilibrium, in other words, being equal on both sides. And so what happens as this CO2 depleted gas moves up the column is you lose the driving force. And so how do you capture 100% CO2 in the system? You don't. If you were to try and capture all the CO2 and truly have CO2 free gas out, it would require an infinitely tall column and would require an infinite cost. And that's why when we get to say 95% capture up to 99, the costs tend to go infinite, okay, and asymptotic because of this natural design, very intuitive. Now, direct air capture. I've talked about solvents and then solid sorbents. And this is just an example up there on the right of what solvent packing might look like. It has to be able to resist corrosion because the solvents, as I mentioned before, and we'll talk a little bit about this, but solvents may have 30 weight% of a base, like an amine, which is a weaker base, versus a potassium hydroxide, which is a stronger base. And so these materials actually have to be able to withstand a lot of corrosion. The solid sorbents look different. If you've ever looked at your catalytic converter in your automobile, they look exactly like this. They're a honeycomb structure. And in that honeycomb structure, what happens is you've got these channels, and the channels, you know, are actually pretty big. You can see them with your eyes there. And the air is able to move through without a whole lot of effort in terms of pressure drop. And the chemistry is anchored onto the surface. And so even embedded into, say, those, you know, sub-millimeter sized channels, embedded is what's called a micro-mesoporous material. And what that means is if you take a single gram of micro-mesoporous material, a single gram has the surface area of an entire football field. And so now when we look at the solvent, when you look at that packing material in this upper right here, and you imagine it, as I said in that previous image, and you can imagine it in this direct air capture contactor too, when you've got that structured packing, what you have to do is the liquid drizzling down has to have a nice even coating. It needs to be coated everywhere. You can't have dry spots. And it needs to be thin because you don't want your CO2 gas to have to go through an effort of getting through and finding chemistry. And unfortunately, the chemistry is only available at 30 weight% because strong bases and bases in general are corrosive. Now, solid sorbents, 1 gram, the surface area of a football field. Very different in terms of the amount of chemistry you can load onto that surface. And so the CO2 has the opportunity in a solid sorbent to interact so much more frequently than it does in a solvent. And so what we're going to learn today is that at the end of the day, if you're for direct air capture, because the driving force is so weak, you need very strong bases if it's to be in a solvent form because of those limitations of the availability of chemistry to interact with CO2. Number one, the structured packing, there's not as much surface area. And then number two, the weight percentage, 30 weight%. And folks are trying to come up with, you know, water lean solvents and things like that, which is interesting. But the end of the day, solid sorbents for direct air capture, you can use weak bases because of that decoration of the surface with so much chemistry. And so you can get away with it. Every time CO2 is in the vicinity, it reacts. And so these two different chemistries are critically important, and it sets apart these two technologies in terms of the energy requirements, and not just the energy requirements in a order, you know, in a magnitude kind of way, but the quality of heat, whether it's low temperature or high temperature. And that's a critical piece. So these look very different. So if I were to think about how many of these do I need to capture 1 million tons of CO2 per year, I need 10 of these units. And you can see, and we're going to talk about why they're narrow here later, but you can see 200 meters long, I need 10. compared to point source capture. Okay, so the height's roughly the same here, and that's like a similar scrubber to what we saw in the Petronova. You know, the diameter is between 6 and 8 meters, the height's roughly 22 meters. You need 2 of these compared to the 10 to capture the equivalent CO2 because of that difference in concentration, difference in driving force. We talked about minimum work, and that energy is directly correlated to the operating expenses in a techno-economic analysis. These, calculations associated with contactor area are directly proportional to the capital expenses. So you can see pretty easily, just quantitatively and qualitatively, the difference in terms of costs of concentrated sources versus CO2 in the atmosphere. And everybody says, direct air capture is energy intensive. And they like to do these back of the envelope calculations, which I'm going to do here, actually. But I always caution against them, but we're going to do it here. And I'll, of course, do it with a caveat. And so, what are these energy requirements? And some can argue a little bit about these numbers. This is work from our Academy of Sciences study from 2019 and from Jan Wurzbacher and his team at Climeworks, who published this paper in our new journal that we launched. This was the launch, and they published in there. And so these are consistent. And so for today's leading technologies, to remove 1 million tons of CO2 per year requires about 500 megawatts of steady power. Now, this is distributed between thermal and electric. And so today, these two approaches that I'm going to be talking about, solvents versus solid sorbents, today, they're driven thermally primarily. It's like that regeneration energy to break the carbon chemical bond. It really dictates the total energy pie. And the thermal piece is significant total of the energy. 20% in some cases, like the adsorption AD with the adsorption is, you've got fans and you might have a, vacuum pump, and then in terms of the solvent-based approach, you have also, fan power and pumps for the liquid solvent pumping and these types of things. But the energy for the electric bit is about 20% compared to really driven by the thermal. And then you have to think about, and we'll talk about it too, is like, well, how do you link this up to low carbon energy, in terms of power or electricity, electrons versus maybe steam. And so that's also important in terms of incorporation. And then I will come back to this, the quality of heat, how hot, right? That's really important. We actually noticed this is super important with industrial decarbonization too. Like, how hot does it need to be? Can we use concentrated solar, for instance, or do we need something hotter than that? And so we'll get into that. But first, let's talk about energy, land, and water requirements. So again, the back of the envelope that people like to do is they like to take, and I'm about to do it, they like to take that 240 to 500 megawatts, and then they like to say, oh, we need to get to a gigaton. Wow, that's a lot of energy. So let's do that. Wow, that's a lot of energy exercise. So this is chapter 1 of the primer again. And so what we did here is we wanted to compare, metrics for energy, land, water, and materials for direct air capture, and then compare it against afforestation and reforestation. How much land does it take? If we want to, and this is all for the calculation to achieve 1 gigatons of CO2 per year removal. So in terms of the energy, when we look at afforestation, reforestation, we're talking about, trees harvesting energy from sunlight and natural processes. The solvents required to capture a gigaton. So again, going back to those numbers, roughly speaking, it's a split too between thermal and electric. And it turns out for the solvents, the quality of heat is 900 degrees C. And then for the solid sorbents, it may be 80 to 100 degrees C. And at the end of the day, when you look at that gigaton of energy requirements, it's pretty significant. And so when we look at our world energy consumption in 2019 of being 19,000 gigawatt years in terms of units, and then you look at solvents being 258, solid sorbents being 187 to 238, it's just so significant, when you do that back of the envelope. And that's where so many people worry, because you ask the question, well, wait a minute. We need to use our low carbon energy to displace, the unabated power generation that we have on the grid today. And we have to be careful. We have to prioritize that low carbon energy like wind and solar and hydro and nuclear for, decarbonizing the grid first and foremost. And so one often gets caught in that trap of saying, do we do direct air capture or do we decarbonize our grid? And so some of the, I think, creative approaches that we're going to get to today will explain how you don't have to choose between those two necessarily. In terms of land, when we look at how you choose how to power the direct air capture facility also impacts how much land we're talking about. And so, and again, you can kind of compare this also to the same amount of carbon removal from a well-managed forest. And so when you look at the area, you also have to recognize a little bit, if you were to power a direct air capture facility with natural gas coupled to carbon capture, the footprint is much smaller than, say, solar. But at the same time, you have to be careful about natural gas, which comes with its own challenges in terms of the fact, if you're doing natural gas coupled to carbon capture and storage, and you're using that energy to fuel your direct air capture plant, for every molecule that you capture from the atmosphere, you have to manage an additional 2 from your natural gas plant. And now you've got to manage 3 at the end of the day. And so your carbon management effort becomes so much more significant if you could have just used low carbon, renewables in the first place. And so we also have to recognize that natural gas is not leak tight today. And so there are methane emissions associated as well. So that whole, balance needs to be examined carefully. In terms of water, this is often misunderstood. And so solvents, depending on where they're placed, depending on the humidity and conditions of climate in that region of where it's located, or I should say weather of where it's located, you may get losses of water. And but in the case of solid sorbents, you're not just absorbing CO2, but these materials can also take up water. So at the end of the day, a Climeworks project or plant is potentially a net producer of water. And then also the materials requirement. This is significant. The amount of solvents that are required, the amount of sorbents required compared to, say, reactive nitrogen today. So for instance, ammonia for fertilizer. And it gives you just a sense of the scale, the chemical industry that's going to be required to doing this at scale and scaling up. So why do some direct air capture processes require low and others high temperatures for regeneration? I've talked about this a little bit, but it's all in the chemistry. The good news is there's only 2 types of chemistry. There's carbonate, which means carbon-oxygen bonding, and there's carbamate, which is carbon-nitrogen bonding. So properties of strong bases, this is the carbon engineering approach, uses a potassium hydroxide. They started off with sodium hydroxide a while back. Now they're focused on potassium hydroxide. Issues are that it's corrosive. It binds so strong that it takes that, we're going to talk about it a little bit, but ultimately at the end of the day, it requires really high quality heat for regeneration. The positive of potassium hydroxide is it can scale up very easily, and we can leverage existing large scale up separation processes today, like what we've learned from Bottoms in the patent from 1930. Properties of weak bases, they're still corrosive, weaker binding, harder to scale up because they're based upon these solid sorbent materials, which, as I showed from the previous slide, we need to be able to scale up. Also, I wanted to recall this point that I made previously, this distribution between thermal and electric. And in here, I'm bringing this back because that back of the envelope calculation, we really have to be cautious when we do that, because at the end of the day, those three kind of boundary conditions that I outlined for the minimum work calculation, one of those parameters was what's the ending purity. If you're assuming that you're going to transport it and inject it deep underground, it's going to be 99% plus purity. But what if you use the CO2 as a chemical feedstock? What if you use it to react with calcium to produce a carbonate that could be used as a synthetic sand or gravel for concrete? What if you feed the CO2 to algae and do something with the algae downstream? In those cases, the CO2 doesn't have to be high purity. And so some work that we did some years ago, we showed this. And again, just using those simple, minimum work calculations, and there's the equation there. And so what I'm showing here is direct air capture and showing the end purity, and then the percent capture ultimately. And then the minimum work is the color scale here. And so what you see down here is this little sliver. The importance of this little blue sliver is that that color overlaps with some of the colors here for natural gas combined cycle and pulverized coal combustion. And why that's important is because there's a parameter space by which the energy for taking CO2 out of the atmosphere is equal to the energy of taking CO2 out of one of these more concentrated sources. And you remember this one's 100 times more concentrated, coal's 300 times more concentrated. So what does that parameter space look like such that the energies are equivalent? And those parameter spaces are essentially when you only need to capture, a smaller percentage of the CO2, either a smaller percentage of the CO2 and ultimately a lower purity. And so just looking at some of the applications, again, transport 99% plus, but mineralization, maybe you only have to concentrate it to 15%. For algae, maybe you're only concentrating it to 5 or 20%, and the energy demand changes significantly. And the nice thing about direct air capture, again, provided that it's co-located with low carbon energy, that shouldn't be first prioritized for decarbonizing the grid, say. The nice thing about it is you can place it next to your algae plant. You can place it next to where the minerals and the feedstocks are for mineralization. You can really be strategic in terms of its co-location. Here, I just wanted to talk a little bit. So on the left-hand side is the air contactor unit on a small scale up in Canada for carbon engineering. And then on the right-hand side, this is Klaus Lackner's cartoon of his approach. And they now have some of these devices on one of their rooftops on campus at Arizona State University. And you might, you hear all of these arguments of direct air capture, maybe $600 a ton, maybe even $1,000 a ton. And then you hear Klaus saying that his approach is less than $100 a ton, and it gets really confusing. But when you start to actually put it in the context of the boundary conditions, you notice that what Klaus's group at Arizona State's doing is actually only increasing, going from 410, 415 parts per million of CO2 in the atmosphere to 1%, and then ultimately 5% to feed it to algae. And so when you go back to that energy space, you realize, well, you can use a really weak base to do this. In fact, and he even used a humidity swing, which means, in an arid climate like Arizona, you can actually, put humidity across these materials in order to kind of drive the CO2 off. So it's a very cheap way to do it because of the application at the end of the day is unique. You're not concentrating it, you're not moving it, you're not doing geologic storage. And so many people start off in this field and they get lost quickly because there's all of these ranges of costs. And so it's easy to get confused. And so I wanted to be really clear about all of those boundary conditions. It really depends on what the boundary conditions are and ultimately what that final purity is. So I want to walk us through a little bit of the carbon engineering process. And I mentioned it before, this is a hybrid approach. And so what I mean by that is it takes into account two different types of separations, which is what makes it a little bit complicated. There's a solvent-based approach, or there's a solvent-based step, and then there's a crystallization-based step. And so what you have is you have your air contactor, which we've seen plenty of. Your air comes in, you have fans to overcome the pressure drop through the beds. And then you have a liquid potassium hydroxide solvent that's trickled over. And so it's a very strong base, so again, probably 30 weight percent. And then what ends up happening is, and potassium hydroxide is soluble in water, which is great. But now, when you produce your potassium carbonate, you got to figure out how to get it back out of solution. And so what they do is they add a calcium hydroxide, and that's called like a chemical swing. And so the reason for that is that chemical reaction, what's happening is the calcium's reacting with the carbonate to produce a calcium carbonate, which can crystallize out of solution. And that's why crystallization is the separation process, because that's the step that allows you to get CO2 out of solution. the downfall of that is you've just produced limestone, and we all know how energy intensive cement making is, and that's essentially what they have to do over here in a calciner. And so you ultimately have your calcium carbonate, which you have to heat to 900 degrees C. And, and you've got these nice recycle streams. Now in Canada, they have, they always say, well, we've tested each one of these pieces and there's nothing new here. And these are kind of off the shelf. We know how to do these. And that's true. So they've tested their unit operations in individual bits and interesting, results and good results. But what they're trying to build in Texas now is the first time ever where they have to get all these pieces working together in a coordinated and integrated way. And so that will be the interesting piece that will be revealed. This is just a little bit more and of the same process, just in a different way. Costicizer is another name for the pellet reactor, which I think is a little more user-friendly. But it gives you some of the details and the data, and you can get all this in the Academy of Sciences or their Joule paper. And but it gives you a nice sense of like, what's the water makeup? One thing that's going to be really critical is that as we do this work, as we demonstrate these technologies and we run them for thousands of hours, it's going to be really important to understand how the solvent holds up in its structured packing over time, given that it's a really strong base and it's really corrosive. And every once in a while, it might lose its efficacy and it may need to be recharged in order for it to fully work. And that's where to me, a lot of the demonstration work is going to feed back into the R&D, of figuring out coatings, of figuring out recharge, of figuring out recycling. But we won't even know what those questions are until we start to operate these things for like months to years to really start to collect that really relevant and important data, which will feed back into R&D. When you look at the solvent-based approach, so the carbon engineering-based approach, and you kind of look at the pie, and this is just energy, not the operating, but so related to the, the energy and the energy OpEx in the end, you notice that a big piece is all in that calcination, and so when we think about maybe in the future developing waterfall plots and where can we really advance and invest in R&D to drive down costs, we should be looking at the big wedges, here. And so where is the big wedges in terms of, one might say, I'm going to develop a better packing material to reduce pressure drop. It's like, well, it's 6% of the energy pie. Is that where we want to spend our time? So we really need to be thinking about these big wedges. So a paper that my student, Noah, published in Frontiers in Climate, and again, that's that negative emissions technology journal that we talked about. What they did is they took that carbon engineering process and they said, imagine in the future, rather than having an oxy-fired calciner, which by the way is what they're running up in Canada, rather than having an oxy-fired calciner that feeds natural gas, what if we were to develop an electric calciner? So there are technologies out there that are pushing electric calcining for low carbon cement. Can we piggyback on some of that? And then in that case, it's kind of interesting too, because you can directly couple to renewables, although you need to think about battery storage because these are not good for shutting down. They can't turn off and on very well. And so just looked at it, the base case, which is how they operate today with natural gas, combined cycle for the power generation for the electricity system, but then looking at, all of these aspects too, if we were to move with an electric calciner. The only thing I wanted to point out here is that when we do look at, natural gas, in the case of natural gas and the use of it, we have to be really careful because depending on the leakage, and there's various estimates out there, in terms of leakage, most recent work of Alvarez, for instance, which is now in the Argonne's GREET model, it's about 2.3% leakage associated with natural gas production in the supply chains today. Now, keep in mind with carbon removal, these carbon balances are so important. And so that when we draw the big box and we care about carbon removal and we estimate the costs, we don't want to estimate costs just based upon the how much carbon we took out of the air. We need to estimate it based on net carbon removed. So if you're using a fossil fuel to feed in to your direct air capture unit, at the end of the day, what is the greenhouse gas footprint across that whole system? if you were to use natural gas and assuming methane, emissions, even on a global warming potential of 20, your cost can go from, say, $232, which they report in the Joule paper, into the 400s quite quickly. And so we do need to be thinking in a really responsible way as we analyze the techno-economic analyses of these applications to really understand, as they're building out the framework today, these units aren't just financed over 20 years, but we hope that they're operating for 30 years or more. And so we really need to be understanding of what's being locked in as we think about these approaches. Walking through the solid sorbent-based separation process, and this is important because I want to distinguish between two companies. One is Climeworks, and that's what I'm kind of showing here, but it's cartoony, so all the details aren't here. And another one is Global Thermostat. And so here in adsorption, and remember now you've got that football field in your mind of a gram of sorbent with all the chemistry and the opportunity for CO2 interactions. And so you have that, monolithic system, kind of like your catalytic converter, where the air is going through and the chemistry interacts and CO2 is captured. And then you have a second step that's desorption. And, really for that regeneration, again, thermally driven 80% of the energy pie, and using, most of the time it can be low quality steam because it's a weak base. It's an amine in this case. And so that steam, now what I'm showing here is, heat exchange. But remember, I said it briefly, but I talked about when we think of limestone or when you think of, a kiln, when we make cement, you're often mixing the fuel with the mineral in order to have a good interaction, to get the heat transfer to happen quickly. When you have to deal with a material and the heat exchange, you get some loss, in terms of the heat movement across the system. With the Climeworks, they have, their monolith is protected. And so they have to do the heat exchange and they get a little loss across that system. So again, R&D interests there. But the thing that they gain, although they lose something in that heat transfer, what they gain is the fact that they're protecting their chemistry on the surface. They're not losing that anchored chemistry. They're not getting loss of amines to the local environment, which is huge. And that's one of the limits and challenges too with the solvent-based approaches, is making sure that there's not misting or, aerosol formation, because these are outside and, exposed to conditions. And so here it's like the chemistry is protected, just the heat transfer is something that, and what it ends up meaning at the end of the day is you have to build your system accordingly. And so it's going to be, a little more, significant to capture equivalent amount of CO2 compared to, say, global thermostat. With global thermostat, there's a direct interaction between that working fluid and the chemistry of the surface. And so in that case, you get wonderful heat transfer, probably lower capital because you get a smaller system. But there's pros and cons to really all of these approaches. And now I know I've been talking for a while and I still have a fair amount of material to go through. And I'm going to try and pick up the pace a little bit and still save some time for questions. I've talked about everything that's in blue here is something I've already talked about. And so what I'm going to do now is talk about the things that aren't in blue and just give some examples. Actually, the one thing I didn't talk about is the last bit, the contactor spacing. One thing that we need to think about is that, if you're starting off with a direct air capture system, and you're thinking of, that first unit that's probably at a smaller scale than you ultimately want to be, maybe it's tens or hundreds of thousands of tons, but you need to be thinking about kind of the balance of plant of scaling up to 1 million tons of removal, because that's really what we need. And so one thing that I showed before, the 1 million tons and how many of those contactors, 10 of them at 200 meters in length, how do you space them over the land? In order to maintain the driving force, which, by the way, is still pretty low, as we said. And so the spacing and the placement and the design of the contactors has to be thought about, early on. Because if you've got a contactor, it's depleting the air. Most of these are designed for, say, 60 or 70% capture of CO2 from that airstream. And so it's like it's depleting it. How far does the next contactor have to be spaced in order for that driving force to be maintained? And so actually the land area and thinking about the configuration of the contactors is an interesting question. Wanted to talk briefly about the interplay between solubility, diffusion, and kinetics. So in chemical engineering, there's two types of kinetics. There's the how fast does something actually move, and then there's the how fast does something react. And oftentimes the diffusion kinetics dictate. And the reason why that's important is because this is a field that requires more than the chemist in the lab developing the next new chemistry. It's so important that the chemists and the chemical engineers and the material scientists and mechanical engineers are actually integrated and working together, because those bigger systems in the end is really what we need to ultimately work on. So really brief, this is too much detail for the amount of time I have. So I encourage you, if you're interested in this, there's the reference down below from 2014. But what I wanted to show here, that's the flux equation. And I talked about this previously. And so the flux, remember, is an interface, and it's the amount of CO2 across that interface per unit surface area. And this is an equation. It's an equation that you can use to calculate the flux of CO2 from any gas phase into, reacting. Okay, so there's a physical piece and there's a chemical piece. And if the driving force was bigger, we wouldn't need the chemical piece. And so, for instance, in some of the more concentrated streams, like, natural gas processing from the earth, you can just go with physical. You don't even need a chemical reaction. In direct air capture, we've already talked, we need the chemistry. And so CI is an important piece. That's the interfacial concentration, which is determined from what's called Henry's law. And that interfacial concentration is directly proportional to the driving force or the concentration of CO2 in the gas phase. And so if your concentration is 100 times more, greater, it's going to then change what that interfacial concentration is. And the reason why that's important is because at the end of the day, if you are a chemist working in the lab, you want to maybe have some targets, and so if you have a chemical reaction between CO2 and an amine, or if it's a solid sorbent, or CO2 and a strong base, you can actually achieve what's called an instantaneous reaction if your rate constant is of this order that I'm showing below. For natural gas exhaust, you can be four orders of magnitude lower for the rate constant. And the reason why this is important is because if you could achieve an instantaneous reaction, which is called EI here, then that means that you've removed all of the diffusion resistance. And that's huge. And there was a technology that was developed at Lawrence Livermore Labs like a long time ago, where they were looking at these capsules, with the solvents, and they decorated the chemistry around the edges of these capsules so that you would get the instantaneous reaction. And what that does is every time the CO2 reacts at the interface, it goes and you get that driving force to be continuous rather than delayed. The other piece I wanted to talk about is regeneration energy, because again, I mentioned they're thermally dominated. So we should probably know a little bit about the fact that there's some 100% electric methods out there. There's the electric, calciner approach that I talked about earlier, but there's also, you might have heard of this company, Wilcox. And so there's more information in this communications piece in Nature Energy from 2020. But here, what they're doing is using quinone chemistry. And one has to really look at what goes into this and understanding, if there's limitations associated with costs and scaling up. But essentially, this process is using strictly electrons, to, at the end of the day, to regenerate the materials. And so the idea of using only electrons and not having to have thermal means that two really big pieces here. It means you could couple directly to renewables potentially, like PV or wind. The other piece is you can turn these off and on. And so you don't have to worry so much maybe about that battery storage piece. The last thing I wanted to point out, again, this is just thinking about optimization, the pressure drop piece. So what we've learned in the space of direct air capture is that there's this sweet spot in terms of the depth into the bed, 6 to 8 meters. You might be asking the question, why not deeper? Remember the theoretical stages that I showed over here, that the more we penetrate through in terms of, that gas and liquid interface, the cleaner the air is, or the gases of CO2 at the top. Well, the same is true here, except you're going into the bed this way. So as my gas is being, is moving through, as I go deeper and deeper, I'm capturing more CO2. But as I'm getting deeper and deeper, it's also taking more power to overcome the pressure drop in the bed. And so here's an illustration of that. And so if you take an average air velocity of 1.5 meters per second, and clearly this is an outdated slide because now concentrations are 415. And that's when I made this slide, is at 400 ppm. But anyway, as you start to go into the, the depth and make it deeper and deeper and deeper, you capture more CO2, but then you're also increasing in terms of the fan power. And so this is in the appendix of the Academy of Science Study, Chapter 5. But, that sweet spot is kind of, somewhere around here. But the question is, if you are in a situation where the cost of electricity is low, or you truly do have stranded electrons that shouldn't be prioritized to decarbonize the grid, can you overbuild in order to capture more CO2? And that's a kind of an interesting question. Okay, just a bit more. So looking at our approaches to investing across FECM, really working a lot with the Office of Science for the lower technological readiness levels, and excited about coordinated efforts associated with the Earthshots work in that space. And then also investing in across the mid to higher TRL. And then a number, I'm going to just flip through here, a number of materials, a number of material systems. Again, here's where we start to bring in chemical engineering, mechanical engineering, which feeds into the techno-economic analysis. Again, we can't develop materials or chemistries in a vacuum. We need to put them into systems, into processes. Also, we need to make sure that our pre-feeds are distributed in different regions with different climate conditions or weather conditions, hot and dry, hot and humid. We really need to, I do feel in this space that there's part of me that feels like we need to skip the concept of lab under a hood and make our labs outside, and really do this in real time in a real environment. This is work from when I was at the World Resources Institute, and we were just looking at the water losses depending on different locations for the carbon engineering approach, using the data from their Joule paper from 2018. And so here you can see 3 different temperatures and also different locations at different times of the year. And on the y-axis, the water loss as a function of the relative humidity. And you can just see significant differences in terms of when you have a higher temperature and, in different times of the year, relative humidities really impacts, the water loss of the system, and then that makeup water ultimately at the end of the day, especially in regions that may be water scarce. This can be very important. Another element I wanted to bring up is with siting. As we think about direct air capture, CO2 is an acid gas. So we have an opportunity to more than just reduce CO2 from the atmosphere. We have the opportunity to scrub the air of other acid gases like sulfur dioxide. When we develop these materials, and I talk about the catalytic converter, it's a 3-way catalyst. And if you've ever opened up an old catalytic converter, you notice that the upstream end has filled with unburned carbon. And so the 3-way part of a catalytic converter is that it captures the unburned carbon, the particulate matter. It converts, it reduces the NOx emissions. And then it also oxidizes carbon monoxide to CO2. And so only 2 of those are catalytic processes. But the point is that similar to the catalytic converter, our units can reduce air pollutants like particulate matter too. And so when we think about siting direct air capture, I urge us to be creative and thinking about regions like ports, highways, areas that are polluting today, so that we can really do our best to not design these systems in a vacuum, but design them in ways that we can appreciate benefits to communities. So wanted to talk too about some of the mapping work associated with coupling direct air capture to existing utilities like geothermal and nuclear. And I'm going to move through this a little bit fast, but the point is that at the end of the day, If you can piggyback direct air capture with existing utilities, then you don't have to build the power plant to do the work for you. You can piggyback. And so we actually awarded through FECM $11 million, and this is in collaboration with folks in the Geothermal Technology Office and also our nuclear engineering colleagues across DOE, 4 FEED studies. We're really looking at coupling and integrating, trying to integrate direct air capture with these low carbon energy resources that at the end of the day, you're not just producing carbon neutral power, but potentially carbon negative power. And you can learn more about this concept too in the study that was published through Lawrence Livermore Lab, Getting to Neutral study. And in that, when you think about Climeworks and as low as say, what if they're in a region where they can't go as low as 80 degrees C and they need 100 degrees C in terms of the quality of heat? We even looked at a case where you bump that up with a heat pump. So you go back to that concept, am I producing electricity or am I doing direct air capture? There's ways where you can actually integrate geothermal with direct air capture, with the direct air capture being the condensing unit of a geothermal power plant, which you need to maximize efficiency, and coupling to a heat pump to even bump up, but you're using really a fraction of the electric than you would have to use otherwise. The last thing I'm going to show is just a series of pictures with some data. This is from the CDR primer. And there's a chapter that talks about siting, and it's global. And it takes data that was available globally, geologic reservoirs, because you have to think about co-locating direct air capture to where you can manage the CO2 if it's not used as a feedstock. But what if you're injecting it deep underground? What if you're injecting it into basalts or ultramafic rocks? And then also, are you using geothermal? Are you using nuclear? Are you using hydro for the low carbon energy? Where globally are all of these opportunities co-located? And so the maps in the CDR primer, where it's, hashed is where there's lacking, some of these subsets of data, but a lot of interesting opportunities. And here is concentrated solar combined with, electric options like photovoltaics or wind. So the concentrated solar in this case would provide the thermal energy. And then remember, the leading technologies today are about 20% power or electric. And so you see, they need to couple, you need to have the PV and concentrated solar or wind and concentrated solar, and needing to co-locate it to where there's, places for storage. This is a blown up version. And the reason why you see the lines, they look like lines, that's because these are kind of responsible data sets where the concentrated solar would be located along roads and not being disruptive of land that has been untouched by industry today. And so, if you're interested, this is on the left, this is a region in Southern Africa, and on the right is a region in Australia. Also, we focused in different regions, and this is Saudi Arabia on the left and Oman on the right. Interesting part about these parts of the globe, a lot of basalt and ultramafic rocks. The reason why those are interesting, because the mineralization of the CO2 happens in the order of years. When you think about CO2 storage in a sedimentary basin, the mineralization step tends to take 1,000 to 10,000 years. And so ultramafic rocks and basalts have their challenges, but they're also quite interesting. A little more detail in this study of the Arabian Gulf Coast countries, if you want to learn more. And here, I think what's interesting is so much potential for direct air capture. And you look at these countries like Oman and look at how small their greenhouse gas emissions are. In the United States, we measure gigatons. They're on millions of tons, So very small, yet significant potential in this region where you have the co-location of low carbon energy combined with storage. Amazing opportunity, which is, no surprise that these folks are engaging with us a lot on a lot of our carbon removal efforts. Opportunities outside of geologic storage. There's a lot of R&D going into making, steel, carbon, with carbon, of course, like as a feedstock, thinking about that as a feedstock and understanding that in order to really have an impact, you need to think about the gigaton scale. Aggregates is significant, tens of gigatons, to give you a sense here too. When we think about this scale, of concrete. You know, this represents building a sidewalk around the equator 5,000 times, or 1,400 Three Gorges dams. And it gives you a little bit of the scale of what the markets are for this industry. And again, the CO2 could be locked away in a synthetic aggregate that replaces the sand and gravel that goes into concrete. And try not to confuse or conflate concrete with cement. Cement's the glue. It's like the calcium oxide or the magnesium oxide. And then you combine it with water and sand and gravel to make the concrete. There's also a lot of energy going into synthetic fuels. You know, Climeworks is working with Sunfire, you know, where they're doing electrolysis, you know, partnering with Audi, partnering with airports, you know, in Europe to make sustainable aviation fuel using carbon dioxide from the air, from the atmosphere, combined with clean hydrogen. Finally, wanted to end on a couple of these with CarbFix. You know, this is the example I talked about, you know, where they're using coupling with Climeworks and CO2 from the air, and they're mineralizing the CO2 in less than 2 years. And I think that, you know, it's a lot, it's not so difficult to sell some of these ideas in terms of durability and safety when you can actually turn it into a rock at the end of the day. These are some of the pictures from a New York Times article in Oman. This is Peter Kellerman's work from Columbia University, where they're looking at these formations and like peridotite and in situ mineralization. Still a lot of R&D in this space. Finally, mine tailings, a lot of opportunity. We've already ground the rock down. Oftentimes they're stockpiled and they are rich in calcium and magnesium alkalinity that could be reactive with CO2 to form synthetic aggregates. And, you know, De Beers, for instance, is leaning in and wants to be the first sustainable diamond mining company. And so you're seeing huge opportunity in this space as well. To learn more about the newish first of a kind journal on carbon removal, more information here. And I'm going to go ahead and stop there and just take only about 10 minutes at the end of the day here to answer any questions that you might have. And thanks for being here. I know that that was a lot of information. And I don't see any questions in the chat yet. The good news is we're also recording this. And so I know I presented a lot of information. Okay, Sarah.
Hi there. Thank you for such a fabulous talk. I mean, really improved my understanding a lot. I was really excited about the work at Arizona State with this kind of small scale direct air capture feeding algae. And that seems to me to provide a really interesting kind of distributive model for direct air capture. And I'm wondering what you think about that potential, you know, sort of more of a microgrid, community scale approach to direct air capture.
Yeah, no, I think a lot of folks are thinking in this space and trying to, you know, leverage existing infrastructure associated with air conditioning, you know, but I would caution against that a little bit, because remember the energy pie that I showed you, where the pressure drop, which is the fan power, which you see when you see fans and you think that's all the energy, that's a very small portion. So with Klaus's work at Arizona State, the reason why they can do that is because they are using it for algae cultivation. And, you know, when you add up all of the uses at the end of the day, it ends up, I mean, a lot of low hanging fruit today, but at the end of the day, there's no silver bullet. And the other piece is that his approach, he can use what's called humidity swing. And so he can use a very weak binding interaction. And in some cases, even use zeolite type materials like 13X. And the reason he can do that is because Arizona is so dry. It's, if you know the region, there's something called a swamp cooler out there. But like it's so dry that typically a zeolite like 13X takes up all the water and there's no space for the CO2 to bind. But because there's no water in the air, they work great and they're super cheap and commercially available and they scale up. And so interesting approach, but very few regions where it actually could make a lot of sense in terms of like using those physical separations, because you can get away with a humidity swing. Absolutely, Scott. I'm happy to share the deck. I was planning to, because there's a lot of, I stopped sharing, but at the end, there's 3 slides that show books and reports and publications and podcasts and things like that. So I'm happy to share. Any other questions in the last few minutes? I've got a question here. What is the potential of using direct air capture to remove methane? Great question. Yeah. Can we think about approaches for methane separations? Well, I think that some of the frameworks, and what I mean by that is like the structured packing material, but the chemistry is different. That's it. And so when I talked about the 2 chemistries, you either combine with oxygen, which forms a very, very strong, those oxygens are typically strong bases, or you can react with a nitrogen to form a carbamate. And so the chemistries for methane would be different to react with methane. And so you'd have to think about those chemistries for methane, but some of the systems-based thinking could apply. Looks like we've got Anjuli.
Yeah, I just have a question. I'm not sure I fully understood it. It seemed that to lower the minimum work requirement, the proposal was to target a smaller end purity. And I'm wondering if what that means. Does it mean that more of the carbon remains in some other stream?
Yes, great question. So number 1, we'll never control that minimum work. It's based on the first and second laws of thermodynamics. But what you're saying is, how about changing one of the boundary conditions? And so there's only 3 things that you need for that calculation. And one of them is the end purity. And so what does that mean? If you've got a gas mixture that's 99.9% pure in CO2, so imagine it's in a box and you've got a box full of molecules and it's CO2 and air and it's 99.9% pure, it means like out of the 100 molecules in the box, only 0.1 is nitrogen and the rest is CO2. Now, if you're at 5% purity, you've got your 100 molecules in the box, 5 are CO2, and there's a ratio of nitrogen and oxygen in air. So most of those 95 are going to be that ratio of nitrogen and oxygen. Ed Rios, yeah.
Yes, thanks. Can you hear me?
I sure can.
Great presentation, Jen. One question I keep thinking about is, as these technologies become more commercial, these facilities start popping up more and more, I'm thinking of how they're going to make money. The 45Q is pretty historic, but it is a regulation that could go away. And the CO2 market obviously is not going to grow it might not grow as fast as these facilities start popping up. So any thought to what's going to keep these facilities going in that kind of
So keep in mind, I dug deep a little bit in this presentation, which means IRA hadn't passed when I developed a lot of these slides. So this $180 federal tax credit for 45Q wasn't around, when I developed a lot of this material, right? And so that's why the emphasis on what can we turn the carbon into that's actually economic and scales, right? And so making sure that there's markets. I think supply chains like low carbon concrete is interesting. The other thing about concrete, and as that's why I had that slide on the scale, you need to think about gigatons. And the thing about concrete is it does lock the carbon away. The other piece is, though, it still needs to be a voluntary market that's willing to pay more for that product at the end of the day. So you've got to think of creative ways. How can you make the concrete a better product? And I think, is there a way to increase the reflectivity so it's not heat absorbing? Is there a way to make it stronger so it's longer lasting? We've got to really think about these types of features that improve the quality. Same with the carbon steel concept too, of lighter, stronger. And it's like, to me, there are some interesting, spaces there without the need for the 45Q. I would also say that this is what drove Climeworks. How were they able to get to the scale they did in the absence of any kind of policy? They did it because they were looking, they boost yields in greenhouses with their CO2, not exactly a carbon removal solution, but they also are doing the synthetic fuels, which offsets our dependence on fossil fuels and crude oil for the transportation sector. So they had other routes in recognizing that there's a voluntary market willing to pay for some of these green products today. And I think we do need to be thinking about those customers. I know we're at time and somebody's asking about direct solar excitation, and photocatalysis is definitely, an area that could be interesting. I think too, in that space, I think looking at photochemistry, where you're bringing the carbon together with water to actually be catalytic to produce at the end of the day synthetic fuels and chemicals, is also pretty interesting. But I'll just end by saying thank you so much for being here, and I hope that this was useful, and have a great rest of the week. Thanks, everybody.